All right. Then we'll finish the last material for the exam. I'll just remind you that we have exam 1 coming up on Monday. And it'll be just during the regular class time, 6 to 7:15, by email only. Don't show up in this room. It is a big room, so if people want to come to class after that, we can probably space out pretty well for the size of the class that it is. You're not required to come. What I'll do is I'll send the test out at 6 o'clock, and then I'll expect it back at 7:15. If you have a problem, though, let me know. It'll be like the extra credit problem that I sent out. Just scan it or photograph it and send it by email to the same address it comes from. It'll be all based on the chapter 9. Unfortunately, due to the cancellations from snow, we aren't quite as far as I'd like to be. The very last section, I'm not going to probably assign problems from, so I may cancel 9.9 on the convergence of Taylor, well, 9.10 on the convergence of Taylor series derivative. So I'm expecting 9.1 to 9.9. There's practice problems on D2L. Not every problem on the test is going to be just like that. Take a look at those, and next time we'll do some review next time while we're here. Hey, any questions on the exam? I don't know which camera to look at in this room, so I'm sorry if I don't look at you. Well, today we'll do some more on series. And we'll start with this definition. We'll say, well, we were doing actually polynomials last time and just introduced the concept of series. So we'll say this, a power series in x minus some number, x naught, is an expression of this form. A dot, I don't think if they use A's or C's now, I'm slipping on most of these. Be nice to use the same notation, wouldn't it? Well, I can't see which one they use, so they mostly did some things later on. So we'll use, I think they use C's, thinking about it. C0 plus C1 times x minus x naught plus C2 times x minus x naught squared plus dot, dot, dot on it forever. It can also be put in sigma notation, sum n equals 0 to infinity, Cn x minus x naught to the n. That'll be called a power series. Right. These are extremely useful in applied mathematics, and here's why. It's kind of hard to see when you just look at the book. When you get solutions that are not just basic trigonometry and algebra expressions, like you're solving a differential equation, which comes in the class after you finish calculus, some sort of solution to a physical problem, if it's not just in terms of standard functions, what do? These can represent a very broad variety of functions. you can get these by adding up a whole lot of terms that converge come very closer, closer and closer to the solution to a physical equation. And so when you don't have a simple expression in terms of the things you know and love from algebra, logarithms, exponentials, polynomials, and trig functions, you go to these to express more general solutions. So that makes them very powerful, but they're also cumbersome because it's an infinite number of terms. You got to decide how far out you want to go to before you have to stop to make it accurate enough. But that's the power of them. They're very versatile for finding solutions to physical equations. Now, in particular, we have this, the Taylor series. For a function f of x at the point x0 is one case of a power series. And it's given when f has derivatives of all orders. And it is a power series. Sum n equals 0 to infinity, just like this, but it has specific values for these CNs. They are the nth derivative of f at x naught over n factorial x minus x naught to the n. That specific power series is called the Taylor series at x naught for f of x. Now you might be able to guess from what we did last time with the Maclaurin and Taylor polynomials why this is so useful. We also need to introduce a special case when, let's call this 1, call this 2. When x naught is chosen to be the number 0, this is called the Maclaurin series. So the Maclaurin series is actually a special case of the Taylor series. And how are these related to the Taylor series, the Taylor polynomials and the Maclaurin polynomials we did last time? Can you see it? The Maclaurin polynomial, or a Taylor polynomial, stopped after you got to the nth power. These go on forever to infinity. So that's the only difference. If you stop after some finite place, then you've got a polynomial of that degree. If you go on forever, then it's a series, a power series. All right. So when n equals 0, this is called the Maclaurin series. And then here's why it looks like what we did last time. We said last time these Taylor polynomials and Maclaurin polynomials as a special case are really neat because they can match the value of the function in x naught, the first derivative, the second derivative, the third derivative, all the way up to the nth derivative by taking the first n of these. Now this goes on forever. Guess what this does? This matches all derivatives. So when the remainder function remember last time was r n of x was f of x minus the nth polynomial, Taylor or Maclaurin, goes to 0 as n goes to infinity. What happens? that means that the errors between the first n terms of this and the actual function get smaller and smaller. In the limit, you get exact equality. We have that f of x is equal to its Taylor series, or Maclaurin series is a special case. Furthermore, that being the case, since we saw the Maclaurin polynomials match through the first n derivatives, this means that this will match derivatives of all orders. You know, if you say, oh, it doesn't match at the billionth derivative, then you just take the billionth Maclaurin polynomial, which is the first part of this, and sure enough, it lines up. And all the other terms are zero because they're higher powers that are zero when you plug in. So also, because they're identical also, all derivatives of all orders aren't necessarily the same since they're the same function. Okay, so what this tells you is something that in the early days of calculators they used to do, not necessarily the series they're going to see here, and do something a little more sophisticated that would, the error would go to zero faster. But you can approximate your favorite function. Like, how does a calculator estimate e squared, for instance? What if I want to know what e squared is? Well, it can do arithmetic and add up a bunch of terms out of the Taylor series and estimate e squared by taking the exponential function e to the x as a Taylor series and then taking enough terms and putting in x equals 2. It can estimate it very accurately. And so this is real nice for function approximation on computers, for instance. All right. Now there's some interesting properties in here, however. The power series whether or not it's a special case of a Taylor series, at x naught, always, this one's hard to prove at this point, so I'm going to have to wave my hands at it. In advanced calculus, you can prove this. It always converges, but you need imaginary numbers to do this, and it takes a while. Always converges either one only when you put in x equals x naught, the point itself. Or on an interval x naught minus r, and I should have said not converges, but converges absolutely. For just the point, or on an interval x0 minus r to x0 plus r for some r greater than 0, called the radius of convergence. And then it diverges for x greater than x0 plus r and x less than x0 minus r, or, don't have room for or over there, so I'll put it here. It converges for, absolutely, for all x. Remember what absolute convergence means? Absolute convergence means the series of absolute values converges. We had that absolute convergence test, remember? So, in the first case, if it converges only at the point, we say the radius of convergence is 0. Usually use r for the radius. In the second case, r is the radius of convergence, whatever that number is that it comes out. Or it converges for all x, and we say the radius of convergence is infinity. Now, this is screaming for an example at this point, isn't it? That's a symbol for infinity. It looks kind of like a Mobius strip. But this is a very interesting thing if you think about it. Remember, any series can converge absolutely, meaning a series of absolute values converges. Conditionally, meaning the series of absolute values doesn't converge, but the series does, or diverge. Right? This says, except at the endpoints where x equals x0 plus r, x equals x0 minus r, the endpoints of this interval, it always either converges absolutely or it diverges. That's a very interesting property of power series. You don't have conditional convergence except maybe at the endpoints of the interval convergence, maybe. All right. So here's a really great series here. One of my favorite ones because it's easy and it's illustrative. One plus x squared plus x cubed plus x to the fourth and so on forever. Also expressible in sigma notation as sum n equals 0 to infinity of 1 times x to the n, right? So each C0, C1, C2 forever is equal to 1. All the coefficients are 1. What an easy series, right? I wonder if it converges, or where it converges. Here are the three cases. Really, the picture makes it better. What we do is we draw on the x-axis. We say we can put in any number x we want into a power series, right? It's just this a sum like this. It might converge only at the expansion point, x equals x0, x naught, right? That might be the only x value, so you plot that, and not plotting the other ones means it diverges if you put in those values next. Or it might converge on a symmetric interval like this. Here's x naught, and then it converges over here to x naught plus r, but maybe or maybe not at x naught plus r. So it converges here, and it converges the same distance the other way, x naught minus r. So there's another interesting property. It always converges on a symmetric interval. And where it converges absolutely, except possibly at the endpoints. So it converges like that. It converges in this interval of length r. If you think about it, this is a one-dimensional disk, if you will, right? A circle of radius r in one dimension is 2 points r units away, these 2 points. The interior of a circle is called a disk, so it's converging on a disk of radius r, and we say radius of convergence r. That's where the concept comes from. Or you can have it converge for all x, in which case you just shade the whole number line. So here's the x number line in each case. It converges either only at a point, and that's a circle of radius 0, or a disk of radius 0, if you like. And it always converges at a single point, right? Because you just, here's the expression for a power series. Cn x minus x naught to the n equals 0 to infinity. If you put in x equals x naught, then every term except for the first, which when you take 0th power, you take this to be 1. Every term except for the first is 0, and so you're just adding one term, C0. Of course it converges, it's just a number. In the second case, you're adding up an infinite number of terms, and within some symmetric interval, it converges absolutely. The series of absolute values converges. And outside of there, on this part, it diverges. And at the endpoints, I didn't write this down, it may converge absolutely, it may converge conditionally, it may diverge, and it may do something at one endpoint, something different at the other. So what I didn't write in there is what it does at the endpoints, and the reason is that it can do anything at once. But everywhere in here it will converge absolutely. The series of absolute values converges. Now here it will diverge. Why is absolute convergence important? It's not real clear in textbooks, and it's not real important for you to know. The important thing is convergence for you. Does it converge? And it converges in this one-dimensional disk. But for advanced calculus, if it converges absolutely, then you can add up all the terms in any order, which means you can like take two power series and multiply them together term by term and get a new result. And there's other nice things you can do too. And one of them's coming up in the next section. I guess it is important for you from that point of view. You can take the derivative term by term, and that will give you an expression for the derivative of the function. So I guess it is important for you in that sense. All right, so there's the case. Converges at a point in a symmetric interval of the whole axis, and we say radius converges at 0, r, or infinity. Here's a nice example here, and I say, what is the radius of convergence and interval of convergence? Well, we can do it like this. Remember how we had the absolute ratio test. Knowing this theorem, we don't have to do some fancy test. We can pretty much always go to the absolute ratio test. We'll simply take rho is the limit. That's why I said this is the most important one as applies to these power series. It's the limit as n goes to infinity of the absolute value of the ratio of the n plus first term, which is 1 times x to the n plus 1, over the nth term, 1 times x to the n, right? So a power series is an infinite series that has the variable in it, either x minus x0 in each term, right? Here it is. A general series just has a sum of numbers, right? The power series is a power series in which each term has a successive power of x in it. Once you plug in x, then it becomes a series, right? So a power series, you plug in x and get a series, is the idea from this. Now, that series that you get, for what values of x does that resulting series, just the sum of constants, converge? We can apply the absolute ratio test. And let's see, this is limit as n goes to infinity. This is an easy one. Well, it's a nice example. The x to the n cancels n of these, and you just get limit of absolute value of x. And then you say, well, this expression is less than 1 if the absolute value of x is less than 1. This expression is bigger than 1 if the absolute value of x is bigger than 1, right? And so what this tells you then, by the absolute ratio test, is that the series converges absolutely, right? The absolute ratio test, since it takes the limit of the absolute value of ratio, shows that it converges absolutely if this is less than 1. So the series converges absolutely for absolute value of x less than 1, but diverges absolute value of x greater than 1. And you have this picture you're starting to draw for the values of x for which it converges. Here's the x-axis. This, by the way, is a power series at x equals 0, right? Because you can think of this as sum n equals 0 to infinity of 1 times x minus 0 to the n. This is a Maclaurin, well, for now, let's just say it's a power series at x equals x0, right? Because you don't have x minus, because the thing that's taking the nth power is x minus 0 to the n. So it's a power series at x equals 0. That means it's going to converge on a symmetric interval about x equals 0, which might just be the point itself. Here's 0. That'll be the center of the interval, taking that picture over here. But now it says, what is the absolute value of x less than 1? That means you're between plus and minus 1. And sure enough, we got a symmetric interval of width 1. And I should have marked over here on this one, on this picture, R and R, right? The radius of the circle from the center to the endpoint. So this one now has radius of convergence 1. We immediately know also from this part that it diverges out here, just as was predicted by the theorem. Now, what about the endpoints? The theorem doesn't say anything because it can be either anything on the endpoints, depending on what the series is. We need to check the endpoints separately in order to get the interval of convergence. Check x equals 1 and x equals minus 1 separately. What happens when you put x equals 1 into this series? 1 plus x squared plus x cubed. You get 1 plus 1 plus 1 plus 1. And unless you take a separate definition like we saw in the video, this adds up to infinity. It diverges, we say, right? A series is said to diverge if you don't add it to some finite number. If it goes to infinity or it doesn't sum out any number, we say it diverges. So it diverges at 1. We'll leave this circle open. At x equals minus 1, we get, let's see, 1 plus x is minus 1. Plus x squared is plus 1, plus x cubed is minus 1. And that doesn't add up to anything, so we say it diverges. So this actually is the interval of convergence that we already drew. We don't have to fill in any points. If we found it actually converged an endpoint, then we'd fill in the dot there. Some people may be more used to this notation. Some textbooks prefer to put these kind of braces for closed intervals. And these kind of braces for open intervals, you're welcome to use those, in which case we'd use minus 1 to 1 like that, with 0 in the middle. So this will be the way you draw it if you use that notation. I'm not crazy about that notation, but it is in a lot of textbooks. This one's more popular, I think. Any questions on that one, anybody? Sort of the simplest example. I have a good question for you. It's adding up to a finite number. What number is it adding up to, do you think? It's a function of x, right? If I put in a number x, I get out a number. I put another number x, I get out a number. That, by definition, is a function, right? When you put in a x and get out exactly one number. So what function is it? We'll just make this additional note because it's useful to memorize this one. If you think about it, you know how to exactly what this adds up to. What is it? Can I figure it out? What kind of series is it? I mean, once you put in a number x, then you find out what the series is. So how can I know what it adds up to? No matter what x I put in, it's actually a geometric series, right? It's a geometric series with, right, a plus ar plus ar squared plus so on, one of those. With a is always the first term, so a equals 1. And R is always the ratio, right? You multiply times R times R times R. So evidently R is equal to X. We already knew how this converged if we would have just realized that for a second, right? We know that the geometric series converges for R between plus and minus 1 and diverges otherwise. So we could have got it that way also in this case. But it verifies what we already knew at least. Didn't come up with a contradiction. That's good. All right. And so, but that does tell us something, right? Because we know the sum of the geometric series, A plus AR plus AR squared and on forever, adds up to A over 1 minus R when absolute value of R is less than 1, and it diverges otherwise on the interval of convergence x less than 1. One plus x squared plus so on and so forth is A1 over 1 minus R x. This is a infinite sum that adds up to our function 1 over 1 minus x. So it's worth memorizing because this actually does come up in practice occasionally. We can call this a theorem. This infinite series, 1 plus x squared plus x cubed on forever, adds up to 1 over 1 minus x if absolute value of x is less than 1, and it diverges otherwise. By the geometric series theorem, and the convergence is also re-verified by what we just did here. All right, so that's one power series. Here's a really neat theorem here, too. Power series on an interval or with radius of convergence greater than 0 are unique. You can't change even one coefficient in the sum and have it add up to the same thing everywhere. You can try, right? If I take this series 1 plus x squared plus x cubed, and I replace x by x plus 0.1, right? It adds up to a different number, right? It adds up to 1 over 1 minus x plus 0.1. I can't cancel it out with one of these other ones here. I'm sorry, if I call this 1.1x instead of, I can't cancel it out by trying to adjust all these other coefficients. Maybe this one's 0.9 now. It doesn't work. It will always have, no matter how you manipulate it, it will always have a different sum for some values of x. So once you have a power series with r greater than 0, it's unique. And this has a very important consequence. Consequently, the Maclaurin series or Taylor series when the remainder function Rn of x goes to 0 as n goes to infinity, is the unique power series for the function. There's only one power series to represent a function if there's any at all. Some functions don't have a power series, it turns out. You can tell that pretty easily, right? One thing you know about these power series, or about the Taylor series, is you have the function has to have derivatives of all orders just to be able to compute it, right? But if you write a function down with a corner in it, doesn't have derivatives there, then it doesn't have a Taylor series at that point. It doesn't even have a first derivative, right? So, but there are actually functions that have derivatives of all orders that don't have Taylor series at certain points also. So the Taylor and Maclaurin series that you write down is the unique power series equal to f of x on the interval. But it has to have a non-zero interval, otherwise it's a point. Let's just say any open interval. So it's not just a point. Now we need another example. This is another extremely important example. Memorize this one. There's certain Maclaurin series and Taylor series, mostly Maclaurin series because they're easy to write down, that everybody knows in higher mathematics, and this is one of them. 1 over 1 minus x equals 1 plus x squared plus x cubed. So you should have that one memorized for the exams, including this exam in a week. So let's try this one, our easy function e to the x. This is about the second easiest power series I know. What is this power series representation if I do it at x0 equals 0? How could I compute it? Well, provided the remainder is going to go to 0, it will be the Maclaurin series. So we try dutifully to compute that. Let's call this f of x equals b to the x. Maybe that would be wise. Then I can say f 0th derivative of x just means f of x, that's all that notation means, is e to the x. And we want all the derivatives at x equals 0. So we'll take the 0th derivative at 0, and we get e to the 0 is 1. Then we take the first derivative at x. I guess we could give it this notation. This is true, but you don't usually use this until you get to 4. So the first derivative is just the usual f prime of x, is also e to the x, right? E to the x is its own derivative. So the derivative of first derivative of f of x at 0 is also e to the 0 is 1. And you just keep going, right? The second derivative with respect to x is e to the x because it's a derivative again. So the second derivative at 0 is e to the 0 again, is again 1, and that just keeps going forever. All derivatives are equal to 1. So what does that tell me? About the function? Now we have that the remainder, by the remainder theorem, in absolute value, has to be less than or equal to m over n plus 1 factorial, n plus 1 derivative at some intermediate point c of the interval you're looking at. No, sorry, I'm going to put that in here. Times x minus 0 to the n plus 1. This is the remainder theorem when you choose x equals 0, where m is the maximum absolute value of the n plus first derivative. at an intermediate point C. And C has to be somewhere then between 0 and x, if x is positive, or it's between x and 0 if x is negative. It doesn't matter. What's the bound on? The n plus first derivative is always e to the x, so this is the maximum value of e to the x over the interval. And it's a finite number, right? For a fixed x, it's a finite number. So the remainder is absolute value of e to the x, whatever number that is, over n plus 1 factorial times x, absolute value of the n plus 1. I can drop the 0. I just put that in there to remind you of the range theorem. It's x minus x naught for the n plus 1 in general. But our series is that x naught equals 0. Now this is fixed. This is constant for a given fixed x. And so is this. And so what we have is, so as n goes to infinity, the limit of Rn of x is e to the x comes out because it's a constant, limit x to the n plus 1. X is a constant here because we're letting n go to infinity. Well, what is this? We did this before. If you have a number to a power over the factorial drives the quotient to 0. So this one we recall from before goes to 0. The factorial grows faster than any power. And so the limit is actually equal to 0. So this is actually going to get us the power series for e to the x. A power series converging to f of x equals e to the x for all x, right? I let x be arbitrary there. Unlike the 1 over 1 minus x function where it doesn't converge for all x, here the remainder goes to 0 for all x. So now we can write it out. Hence, the Maclaurin series, we have to go back to 2 here, or maybe it's 3. I can't remember. 2 was the Taylor series. I think I wrote 3 separately for Maclaurin. The Maclaurin series 3 is e to the x equals, and here it is written out, right? It was f0 of 0 plus f prime, let's try f of 0, plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed plus on forever. It looks exactly like the Maclaurin polynomial from last time, but it goes on forever. You don't stop at the nth one. That series just goes on forever doing the same thing. So that's the Maclaurin series, and it's actually equals. So I'll write equals here, and we say that that e to the x is represented by this Maclaurin series. So these are actually equal then for all x. And this is the unique series that does it. But what is it? Well, now we put in that e to the function at 0 is 1, the derivative at 0 is 1, the second derivative at 0 is 1. So we can put in that all these derivatives are 0. This is 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And here is an infinite power series that converges exactly to e to the x if you just carry enough terms. And it doesn't matter how big x is, or positive or negative. It works for all x by the argument there that the remainder term goes to 0 for all x. So it's pretty complicated stuff. to figure out all those details. I just want you to see it and have a feeling for it. But when the remaining terms go to 0, this power series converges to the function for those values of x for which the remainder went to 0. And so we call that the Maclaurin series or Taylor series for that function. And here we found that e to the x has a power series that represents it for any real number x. You just plug that in. And what happens in practice is that if x is really big, then you have to add up a whole lot of terms to make this accurate. Right? You might have to add up a Google terms or something, but it'll eventually be as accurate as you want because the error is driven to 0 eventually. But if x is really small, like 0.1, then you get 1 plus 0.1 plus 0.1 squared is 0.01 over 2 factorial, 0.0001 over 3 factorial. Then the difference in the terms will drop off quickly, and this will converge without adding up so many terms. So x small in this one doesn't take very many terms to get an accurate estimate. X big, you have to add a long time, is the drawback. And the idea is, in general, convergence requires, you get better accuracy sooner with less terms when x is near the expansion point, we call it x0. In this case, since we use the Maclaurin series, x0 equals 0. But eventually converges for all x in this case. Just takes more terms. So there's the power series for the e to the x. What we were doing for the Maclaurin polynomial, just adding on forever. Sometimes you have a power series that doesn't go with any particular known function. You still might want to know where does it converge, right? So we can try some more examples of convergence for general functions, for general series. We just appeal, usually, to the ratio test for absolute convergence. Just like we did in the first example. Since we know wherever it converges, except possibly at endpoints, it's going to converge absolutely anyway. We don't lose anything with looking at that. So here's an example. Suppose I gave you this one. Find each interval and radius of convergence. Sum k equals 0 to infinity, x to the k over k plus 1. How about that? Again, you just, by instinct, go to this the first thing. So this will be the limit as n goes to infinity of the n plus first term. You just replace k by n plus 1 and put x to the n plus 1 over n plus 1 plus 1. Just everywhere you see k, put parentheses and put in n plus 1. And on the bottom, you just replace k with n, x to the n over n plus 1. There it is, the ratio of the n plus first term to the n. This is the limit n goes to infinity of top times bottom is n plus 1 x to the n plus 1 over middle times middle, x to the n times n plus 2. Let's see absolute value. X is fixed within this, so it can come out, right? The nth power and the nth power cancel. And you wind up with absolute value of x can come out because it's not in the limit. Constant within the limit. And you have n plus 1 over n plus 2 that can't come out. And I can drop the absolute values because, right, n is a non-negative number. But what's this limit, n plus 1 over n plus 2? We know that. It's the ratio of dominant terms, right? They're the same power, so the limit is 1. So rho equals absolute value of x, we drop this 1, is the rho from the absolute convergence test. Therefore, we converge for, and it converges absolutely for absolute value of x less than 1, because that'll make rho less than 1, diverges for absolute value of x greater than 1. And so that tells us that we're looking at this interval again, just like we did with the series 1 plus x squared, etc. From 0 over to 1 and back to minus 1, the radius of convergence must be 1. Converges on this interval. Then we have to check the endpoints separately. So radius of convergence is 1. I should point this out. Whenever you have x minus x0 less than r, this is a circle of radius r. It means it converges on the interval x0 minus r, x0 plus r. So this inequality means this interval, if you think about it. It means the difference between x0 and x is less than r, so you go r to the right, r to the left, say it has to be in between here for this difference to be less than r. Anyway, so we have radius of convergence 1, and we check the endpoint separately by checking at x equals 1. What do we get for this sum? We get sum k equals 0 to infinity of 1 to the k over 1 plus 1. Oops. So k plus 1. It's the sum. When k equals 0, you get 1. When k equals 1, you get 2, 1/2. When k equals 3, you get 1/3. Does that look familiar? Do you recognize that one? That's our front of the harmonic series, right? We know that adds up to infinity. So it diverges, right? Not a finite number, we say it diverges. Then we check at the other point at x equals minus 1. We get for the series. Now we can put in x equals minus 1. Sum k equals 0 to infinity minus 1 to the k over k plus 1. Sometimes it helps to write out the first three terms. You put in k equals 0, you get minus 1. I'm sorry, minus 1 of the 0 is 1 over 1. So you get 1. Put in k equals 1, you get minus 1 to the 1 over 2. So I get minus 1/2. Now I get plus 1/3. minus a fourth, and it alternates sign because of this minus 1 to the k. What's that one? Anybody? That's familiar too. That's the alternating harmonic series, right? If you change this to minus, plus, we call that the alternating harmonic series. And the interesting thing of that was, even though this one, the terms don't die off to zero fast enough, it converges, it adds up to infinity. If you alternate signs, it does add up. It adds up to natural log of 2, maybe you remember. Alternating harmonic series. It converges. It converges conditionally, actually, because it's a series of absolute values is a harmonic series. But it converges. So if you put the interval of convergence, you include the point minus 1 this time, we'll fill in the bubble. And so here's the interval, because we first checked by the absolute convergence test that this is the interval, minus 1 to 1, except for the endpoints we don't know. And then we check the endpoints separately, and we fill in the one where it converges, leave open the one where it doesn't. And so this is the interval of convergence. And this is the radius of convergence, this is the half width of the interval. All right. So they're kind of tricky. You just have to practice these. And we'll do some more of these next time. There's an example where it converges at one endpoint, not the other. These are really nice like this. You'll like these. You probably, once you get a little intuition for these are not so bad. Again, it's like practicing a sport. Once you get good, it comes naturally, right? So if I see something like this, I know immediately. This is the sum 3 to the k over k factorial x to the k running from 0 to infinity. Same question. This will be, I said find each, so this is A, this can be B. We do the same thing. We apply normally the ratio test for absolute convergence. We take the limit as n goes to infinity, and on the absolute value, and on the top we put this with k replaced by n plus 1, so we get 3 to the n plus 1 over n plus 1 factorial x to the n plus 1, and on the bottom we put it just as it is with k replaced by n, 3 to the n over n factorial to the n. So this is limit n goes to infinity of, and we take top times bottom over middle times middle again, 3 to the n plus 1 times n factorial times this goes on the top with the 3, so it's x to the n plus 1 over bottom times bottom, including this one because this goes in here. 3 to the n plus 1 factorial x to the n. And we can cancel a lot of stuff. Remember, when there's powers and factorials, things cancel nicely. Let's rewrite this as limit n goes to infinity of, we'll write 3 to the n plus 1 as 3 to the n times 3. We'll write x to the n plus 1 as x to the n times x. And on the bottom, I'll write 3 to the n. I'll write n plus 1 factorial is n plus 1 times n factorial, right? This is numbers 1 through n multiplied together times n plus 1 makes n plus 1 factorial. That's a major trick. N plus 1 factorial is n plus 1 times n factorial. And then I've got on the bottom still an x to the n. So I rewrite it like that. Now things cancel. X to the n cancels x to the n. 3 to the n cancels 3 to the n. N factorial cancels n factorial. And I have limit n goes to infinity of 3x over n plus 1. What's that? This is actually easy once you know what you're doing. But the trick is saying it. 3 and x are both constants, right? We're just letting n go to infinity. So we can pull the constant out and say this is absolute value of 3x times the limit n goes to infinity absolute value of 1 over n plus 1. I don't need the absolute value because it's positive. 1 over n plus 1. What's that? Top is going to 1. Bottom is going to infinity. Remember, if the power on the bottom of polynomial over polynomial is bigger, then the limit is 0. So 1 over infinity, this is driven to 0. This limit is actually equal to 0 for all x. It doesn't matter what x is. This one gets smaller and smaller, forcing 3x times that to 0. This is for all x. Therefore, rho is equal to 0 for all x. That means it converges for all x. Since rho is less than 1 for all x, we get convergence for all x. Actually, absolute convergence. We can put that on there if you want. Which means the interval is just the whole x-axis. Just shade the whole thing. And the radius, we say, is infinity. By the way, I should make one comment on here. Sometimes I use this for the real numbers, r with double bars. This will refer to all real numbers, but without the double bars, this refers to the radius of convergence. So don't get this mixed up with real numbers. All right. Book will boldface to real numbers, or maybe make a thing like curly r or something for real numbers. Depends on the book. Any questions on that one? This is what you want to be able to do, is see a power series and be able to find its radius and interval of convergence. I'll show you a real classic example that I won't ask on the test here just for fun. Suppose I have the function, well, actually, let me wait on that. I want to make sure I finish these other important functions. We'll get to it. See, the next one is f of x equals sine x. What are its derivatives? Well, I can take f of, let's do the Maclaurin series. And suppose I want to find what's its radius and interval of convergence for its Maclaurin series. What does this actually give us a good function? A good series for sine x? Well, f of 0, if I do Maclaurin series, is sine 0 is nothing, right? F prime of 0, well, derivative of sine is cosine, so you get cosine 0. That's 1. The second derivative, we did this for Maclaurin polynomials last time. We're just sort of repeating it for the whole series now. But it's important we do. The second derivative of sine is minus the sine, right? First derivative is cosine, second derivative is minus the sine. And so the second derivative plug in 0 is minus the sine of 0. Is 0. The third derivative of sine. Derivative of sine is cosine, derivative of that is minus the sine, derivative of that is minus the cosine. And then I plug in 0, I get minus cosine 0. And I get minus 1. And then I take the derivative of minus the cosine, I get back the sine, I start repeating. This is the third derivative, sorry. The fourth derivative of sine is again sine. So I'll take the sine as 0 and get back 0. And so on, right? Fifth derivative at 0 is cosine. At 0 is 1, and so on. And we just get these four numbers repeated over and over ad infinitum, right? Now, what is the Maclaurin series for sine? I'll just say it turns out, and I don't want you to have to do this on the test. This is for people who take real analysis. If you ever take real analysis, a course called that, it's basically going back and proving all these details we do in here, and then doing a little more besides. But a lot of it is just proving all these theorems that were too much to prove in calculus class. A lot of it is. All right, so it turns out, and I'll defer this to real analysis, that the Rn of x, the remainder between sine x and its Maclaurin series, goes to 0 as n goes to infinity. So this is actually going to have zero difference provided it converges. And we have the series Maclaurin because it's at x equals 0. F at 0 plus f prime at 0 times x. This is for any function. This is its Maclaurin series. It's just this, where you just have to put in whatever f is. This is the definition. For sine function, f of 0 is 0. This one is 1. And then this one is 0. And then this one is minus 1 over 3 factorial x cubed. And you can see how it goes. Then it gives 0 x to the 4th plus 1, put it down here, plus 1 over 5 factorial would be the next one, x to the 5th minus plus 0 x to the 6th. All the even terms go away because all those derivatives are 0. The odd terms alternate 1, minus 1, 1, minus 1, all over the corresponding factorial. 0 x to the 6th minus 1 over 7 factorial, the 7th, and so on. There is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. The Maclaurin series for sine x. I like to memorize it that way rather than the sigma notation. But if you think about it, you should know the sigma notation. It also looks like this. It looks like sum k equals 0 to infinity of minus 1 to the k over 2k plus 1 factorial x to the 2k plus 1. You have to rewrite it a little bit. But this one will take only the odd terms, right? When k is 0, the bottom is 1. When k is 1, the bottom is 3. Then when k is 2, the bottom is 5. And so the bottom here gives odd factorials, and the top here gives odd powers of x. If you add it that way, it gives precisely this. And the minus 1 to the k makes the plus, minus, plus, minus. Except, let's see. It should be k plus 1 here. So the first term is positive. That's the Maclaurin series in its easy to remember form and in the important sigma notation, so you can use that later for special applications. And we'll say similarly, pretty much all of your standard functions from trigonometry and algebra have series that converge at least on some intervals, some on larger intervals than others. For instance, the cosine of x, if you do exactly the same analysis, comes out to be 1 minus x squared over 2 factorial. It takes all the even terms, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. It's exactly the same way, plus the blah, blah, blah. And it has this slightly easier sigma notation, but not much. Sum k equals 0 to infinity minus 1 to the k over 2k quantity factorial x to the 2k. Let's see. Oh, I know this was right the first time. I'm sorry. This was minus 1 to the k. Hey, yeah. This is. I'm sorry. That's minus 1 to the k. Here's the cosine series. So you memorize this one, particularly this form. You memorize this one, and you memorize e to the x and 1 over 1 minus x. E to the x was this. Right, it was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah, blah, blah. And it had this nice notation. Sigma notation is easy. Sum k equals 0 to infinity x to the k over k factorial. So that one's to memorize. memorize. And then the 1 over 1 minus x series. 1 plus x squared plus blah, blah, blah with easy sigma notation. Sum k equals 0 to infinity x to the k. Those 4 are the ones I want you to memorize. The others, there's some that are useful. You may want to memorize them, but you have to know these. There's some for tangent and for natural log and all those kinds of things. Some of them converging with infinite radius and some of them not. Sine x, I just mentioned, has radius of convergence infinity. Cosine x has radius of convergence infinity similarly. E to the x we already showed has radius of convergence infinity, so convergence for all x on these, very important functions. This one has radius of convergence 1. Well, only convergence between -1 and +1. Now it looks like it's really hard because once you get an exotic function, you may not have such nice, easy to figure out derivatives, right? Maybe derivatives get real complicated, right? Like maybe I want to find the following. By the way, I've only had you memorize Maclaurin series. People don't tend to memorize very many Taylor series where it's x minus x0 to the end. They usually just memorize when x0 equals 0. So these can be used to memorize other series. And here's an interesting one. You might think this is really terribly hard. Like, what is the series for e to the x squared, right? You might ask the question, wait a minute, is that e to the x quantity squared, or is that e to the x squared? And the convention is if it's this one, then you can pull the 2 down and it becomes this, and so you don't write it that way. If you write e to the x squared, it means this one, right? Because otherwise you reduce it. So e to the x squared, what is that? What's the series for e to the x squared? If you really think about it, a lot of these can be done cleverly like this. Let u equal x squared, right? Then this is e to the u. I know the series for e to the u. It's 1 plus u squared over 2 factorial, u cubed over 3 factorial, and so on forever. Adds up exactly to e to the u. Well, wait a minute, u is x squared, so this is 1 plus x squared plus x squared squared is x to the 4th over, that's divided by 2 factorial. X squared cubed is x to the 6th. And I have deduced a series. How do I know that's the Maclaurin series? Because it's a power series, and power series representation is unique. This one has all the coefficients of odd power 0. It doesn't matter. It's a power series. Power series representation is unique. This is what I would get if I did terrible, complicated derivatives first, second. Can you imagine taking the 10th derivative of this? It would be a mess. But you don't have to. You already know what the series is from doing this. So you can sometimes deduce more complicated series from this one. I'm about out of time, it looks like. Suppose I gave it a series for x, sine x. What is that series, do you think? Well, sine x looks like this. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial, taking alternate terms in the e to the x series and plus and minus on them. You can just multiply that x in and get x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus plus minus plus so on. That's a power series. Power series representation is unique when it converges, and we already know this one does, so this one times x does. This is the power series if you did terrible, complicated derivatives for this. So the object is, with simple functions, you can take all those derivatives and compute the Maclaurin series and get the series. For more complicated functions, you try and do tricks like this. So you don't have to do those messy derivatives. Well, that's all we have time for tonight then. I want you to try these problems then in 9.8 on Maclaurin and Taylor power series. I'm making sure I got the right section number. It'll be these problems. be able to do these for next time. 1 to 13 odd. 19, 21, and 29 to 47 odd. There's a bunch of them, but just if you start to see you can do them all, you can just say, yeah, I know how to do that. But these are the ones I want you to be able to do for the test.
So we'll do 9.9 next time.
Yeah, we'll talk about 9.9 a little next time. I may not be able to put it on the test after all. It's just, we talked about it some tonight, but I didn't get as far as I wanted. It says that if the remainder term goes to 0, then the thing converges. I'm trying to see how much I left out. Yeah, let's just go through 9.8 for the exam then. Yeah, so exam. And I think that's all I put on the practice test. Those sections. Have a good evening, everybody.